For an objective function z is equal to ax plus by, where a and b are positive, the corner points of the feasible region determined by set of constraints, that's a linear inequalities, are 0, 20, 10, 10, 30, 30 and 0, 40. The condition on a and b such that the maximum z occurs at both the points 30, 30 and 0, 40. And since we know that the optimal value that is minimum or maximum must occur at corner point. Corner point of the feasible region, corner point or vertex, we can say vertex of the feasible region. So here 4 corner points are given: 0, 20, 10, 10 and 30, 30 and 0, 40, and the objective function z is equal to ax plus by, where a and b are positive. And now it is also given that we need to find the condition on a and b such that maximum z occurs at 30, 30 and 0, 40. So at 30, 30, at 30, 30, z is equal to, so 30 times a plus 30 times b, and at 0, 40, objective function z is equal to 0 into a 0 plus 40 into b, that's 40b, and the maximum occurs at both the points means the objective function at 30, 30 and objective function at 0, 40 will be the same. Maximum occurs at both the points 30, 30 and 0, 40, which implies that (30a plus 30b), which is equal to 40 times b, or we can write 30a is equal to 40 times b minus 30 times b, that is 10 times b is equal to 30 times a, or b is equal to 3 times a, or we can also write b minus 3a is equal to 0. So the relation between a and b can be found as b minus 3a is equal to 0, which is our option 1. So option 1 is the answer. Okay. For which value of m is the line y is equal to mx plus 1 a tangent to the curve y square is equal to 4x? So there is a curve y square is equal to 4x for which the tangent is, so y is equal to mx plus 1 is a tangent, which implies that it cuts the curve at one and only one point, means equal and real roots, we can say. So let us solve the equations. Y is equal to mx plus 1 and y square is equal to 4x. Substitute y is equal to mx plus 1 in the curve equation, y square is equal to 4x. We will have mx plus 1 whole square is equal to 4 times x, m square x square plus 1 plus 2 mx, which is equal to 4x, or we can write m square x square plus 2mx minus 4x plus 1 equals to 0. That is m square x square plus 2m minus 4 of x plus 1 equals to 0, which is a quadratic equation in which we can say that this line y is equal to mx plus 1 is a tangent, means whose discriminant can be taken as 0 because equal and real roots, real and equal roots, we can say. So that let's take the condition delta is equal to 0, that is b square minus 4ac equals to 0 for the equation ax square plus bx plus c equals to 0. So when comparing, a is equal to m square here and b is equal to 2m minus 4 and c is equal to 1. So the condition delta is equal to 0, that is b square 2m minus 4 whole square, which is equal to 4 into m square into 1. So on simplifying, 2m whole square, that's a 4m square plus 16 minus, so we can write here 2 2s are 4, 4 2 4 is 16m is equal to 4m square. So we can cancel this 4m square on both the sides with the same sign. So 16m is equal to 16, or we can write m is equal to 1. So we can say that for the line to become a tangent for the curve y square is equal to 4x, the value of m can be taken as 1. So second option is the answer. The maximum value of x of x minus 1 plus 1 whole to the power of 1 by 3, where 0 less than or equals to x less than or equals to 1. So let f of x is equal to x of x minus 1 plus 1 whole to the power of 1 by 3, where x belongs to closed interval 0 to 1. So clearly f is continuous function. It is continuous function on closed interval 0 to 1, and f is differentiable. F is differentiable on 0 to 1 open interval, and for the function f, maximum or minimum values occurs, maximum or minimum values of f occurs for the value of x, for the value of x for which f dash of x is equal to 0, or at the endpoints of the interval. So let us differentiate the function and find the value of x for which f dash of x is 0. F of x is equal to x of x minus 1 plus 1 whole to the power of 1 by 3. So differentiating, f dash of x is equal to 1 upon 3 times of x of x minus 1 plus, let us write, simplify and do it. So we can write this as x square minus x plus 1 whole to the power of 1 by 3. So the differentiation will become simple. So 1 by 3 times of x square minus x plus 1 into, again, differentiation of x square minus x plus 1 by chain rule. So we have 2x minus 1, so which is equal to 0 for minima or maximum value. So f dash of x, therefore x square minus x plus 1 equals to 0, or 2x minus 1 equals to 0. So for the first equation, x square minus x plus 1 equals to 0, its discriminant is 1 minus 4, which is equal to negative 3, which is less than 0. So we can say there are no real roots. No real roots exist for this, and also we can say the curve is x square minus x plus 1 is positive for all x belongs to R. It cannot be equal to 0. And now 2x minus 1 equals to 0, that is x is equal to 1 by 2. So if at x is equal to 1 by 2, at x is equal to 1 by 2, we got f dash of x is equal to 0. This is one point to be considered, and the endpoints are x is equal to 0, x is equal to 1. These are the endpoints of the interval. Now let us check the function at these 3 points. Given function f of x is equal to x of x minus 1 plus 1 whole power 1 by 3, x of x minus 1 plus 1 whole to the power of 1 by 3. Now let us substitute these 3 points. F of 1 by 2 is equal to 1 by 2 into 1 by 2 minus 1 plus 1 whole to the power of 1 by 3, which is equal to 1 by 2 into 1 by 2 minus 1 is minus 1 by 2 plus 1 whole to the power of 1 by 3, which is equal to 1 minus 1 by 4. That's 3 upon 4 whole to the power of 1 by 3. So which is less than 1, we can say. and f of 0 value, f of 0 is equal to 0 into 0 minus 1 plus 1 whole to the power of 1 by 3, which is equal to 1 power 1 by 3, it is 1, and f of 1 is equal to 1 into 1 minus 1 plus 1 whole to the power of 1 by 3, that is 1 power 1 by 3 is again, we'll have the 1. So among these three values, so the first one f of 1 by 2 is less than 1, so we can say these are maximum value. At x is equal to 0, we can say at x is equal to 0 and x is equal to 1, f attains maximum, the function f attains maximum, and the maximum value is, which is equal to 1. So we can go with an option, maximum value is 1, so which is third option. Okay. In a linear programming problem, the constraints on the decision variables x and y are given. X minus 3y is greater than or equals to 0, y greater than or equals to 0, and 0 less than or equals to x less than or equals to 3. Then the feasible region is among the four options. So let us draw the diagram rough, and let me consider the inequalities based on the given constraints. So the equations based on this is x minus 3y is equal to 0 and y is equal to 0, and 0 less than or equals to x less than or equals to 3 means x is equal to 0 and x is equal to 3. For x minus 3y is equal to 0, we can see that origin is a point, and for x is equal to 1, so y is equal to 1 upon 3, so you may get the straight line. So this can be considered a straight line. X minus 3y equals to 0. And another one, y greater than or equals to 0. So for y is equal to 0 is the line, x is on x-axis, y is equal to 0. So you can consider this the whole line, y is equal to 0. And it is next one, x is equal to 0 and x is equal to 3. So for the equation of y-axis, x is equal to 0. So this is one line, and another line. Let us consider this is x is equal to 3. And now coming to the region part, x minus 3y is greater than or equals to 0. So we can see the solution part by substituting any one point. Let me substitute this 3 comma 0 and verify it. If you substitute x is equal to 3 and y is equal to 0, 3 minus 0 is greater than or equals to 0, so it is satisfying. The solution region can be taken the lower part of x minus 3y. And coming to the next, y greater than or equals to 0, so y positive in the first quadrant and second quadrant, so we can shade the region in the first and second quadrant and second quadrant. And coming to the third inequality, x lies between 0 and 3 means x is lying between x is equal to 0 and x is equal to 3, so whereby we can shade the region between these two lines, x is equal to 0 and x is equal to 3. Now the combined solution, the feasible region, is obtained where all the 3 inequalities, say this is O, A, 3 comma 0, and here is one more point, at x is equal to 3 we can say 3y is equal to 3, so it is 1, 3 comma 1 point. So these are the 3 points where we can observe that this region is a feasible region, which is found in the first quadrant. So among the four options is bounded in the first quadrant is the answer. Okay, let A is equal to matrix 1 sin alpha 1 minus sin alpha 1 sin alpha minus 1 minus sin alpha 1, where alpha lies between 0 and 2 pi, including both 0 and 2 pi. Then the options are related to the determinant. Let us find the determinant of matrix A. Which is equal to 1 times, so 1 into 1 1, minus of minus sin alpha into sin alpha sin square alpha, it's a plus, and again minus sin alpha times minus sin alpha minus of minus plus sin alpha, and plus 1 times of minus sin alpha into minus sin alpha, that is sin square alpha, minus of minus plus 1, so which is equal to 1 plus sin square alpha plus 1 plus sin square alpha, that is 2 times of 1 plus sin square alpha, and here sin alpha minus sin alpha gets cancelled 0, so we have 2 times of 1 plus sin square alpha. Since we know that sin alpha lies between minus 1 to plus 1, the range of sin alpha is minus 1 to 1, so sin square alpha will be lying between 0 and 1 including both, and then adding 1 plus sin square alpha is lies between 1 and 2, and then 2 times of 1 plus sin square alpha multiplying the inequality with 2, so we'll have 2 and 4, so we can say that 2 times of sin square alpha is lying between 2 and 4, so which belongs to closed interval 2 comma 4, so therefore determinant of A belongs to closed 2 comma 4, so option D is the answer. Now let's check case study problems. So given here, the fuel cost per hour for running a train is proportional to the square of the speed it generates in kilometer per hour. If the fuel costs 48 rupees per hour at speed 16 kilometers per hour, and the fixed charges to run the train amount to rupees 1200 per hour, assume the speed of the train as v kilometer per hour. So first let us write the given information. So the information is given in the problem. Fuel cost per hour is proportional to square of the speed. Square of the speed, it's given per hour. Fuel cost and speed is in kilometer per hour. Let me write here. This is per hour and speed is kilometer per hour. And also it is given fuel costs 48 rupees per hour, 48 rupees per hour at a speed 16 kilometers per hour, and also given the fixed charges per hour. Fixed charges is equal to 1200 rupees per hour. Now let us assume that the speed is v. So the first problem, given that fuel cost per hour is k times the square of the speed of the train. So in 46th question, fuel cost per hour is k times the square of the speed. Speed is considered to be v, so we can write v square in kilometers per hour. And since we know that fuel cost per hour is 48 rupees per hour, which is equal to k into speed is 16 kilometers per hour, so 16 square, so which implies k is equal to 48 upon 16 square. or we can write 48 upon 16 into 16, 16 3 times. So we have k is equal to 3 upon 16. So here fuel cost is proportional to square of the speed, and if fuel cost is equal to proportionality constant k into v square, so we got k is equal to the proportionality constant 3 by 16. So this is proportionality constant. And so we have option, the value of k is 3 by 16, option D, right? Now let us see another problem. If the train has traveled a distance of 500 kilometers, then the total cost of running the train is given by the function. And since we have seen fuel cost per hour is equal to k, we got proportionality constant 3 by 16, proportionality constant 3 by 16 of v square. So this is for 1 hour. Now fuel cost for, let us take t hours, which is equal to 3 by 16 v square into t, and also fixed charges per hour is equal to 1200 rupees. And now fixed charges for t hours, which is equal to 1200 rupees into t. And now if the train has traveled a distance of 500 kilometers, since we know the relation speed is equal to distance per time, so we can write time is equal to distance upon speed. So here distance is given 500, so let us take the distance 500, and speed we can consider as v. So therefore time for 500 kilometers, which is equal to 500 upon v, we can write. So that is t is equal to 500 upon v. Therefore the total cost of running the train for 500 kilometers, which is equal to fuel cost is 3 by 16 into v square into t, that is 500 upon v, plus fixed charges are 1200 rupees into t is 500 upon v for 500 kilometers. So we can simplify this. So we can write here, on simplifying, so 4 times here, 4 125 times 125 3s are 375 upon 4 v plus 12 5s are 60 and 4 zeros, so 6 lakhs upon v. So we got the total cost for running the train for 500 kilometers is 375 upon 4 v plus 6 lakhs upon v. So which is the option 375 upon 4 plus 6 lakhs upon v is second option. Okay, option B is the answer. Now let us see another problem. Now to find the most economical speed to run the train is, since we know that for 500 kilometers we have the total cost to run the train for 500 kilometers, let us take, so which is equal to 375 V upon 4 plus 6 lakhs upon V. This is for 500 kilometers. Now using this relation, let us find the economical speed to run the train. To find the maximum or minimum, so we need to differentiate the function and we have to equate it to 0. So let us consider this as a C function, so that to get maximum or minimum speed, so let us consider dc by dv is equal to differentiate with respect to the speed, dc by dv is equal to 0. So let's differentiate it. (375) upon 4 into 1, and differentiation of 1 upon v is minus 1 by v square, so we can add 6 lakhs upon v square, so which is equal to 0. So whereby we can add 6 lakhs upon v square is equal to 375 upon 4, or v square is equal to 6 lakhs into 4 upon 375, and on simplifying, so we will get 6400 v square value, so which implies v is equal to 80. So therefore speed of the train must be taken 80 kilometers per hour for the most economical speed. For the most economical speed to run the train is 80 kilometers per hour is the best. Okay, now let us see another problem. Now the fuel cost for the train to travel 500 kilometers at the most economical speed. The previous problem we have seen the most economical speed v is equal to 80 kilometers per hour, and now the fuel cost to travel 500 kilometers, fuel cost for the train for 500 kilometers traveling, to travel 500 kilometers, which is equal to, we have solved it, and it is given 375 upon 4v. 375 by 4 into v is the fuel cost, and at the most economical speed we can calculate 375 upon 4 into 80, so 420 times, and 375 into 20 we can write 7500. So we can say fuel cost for the train to travel 500 kilometers at the most economical speed 80 kilometers per hour is 7500. That's option C. Okay, now let's see another problem. Now the total cost of the train to travel 500 kilometers at the most economical speed is, the most economical speed is 80 kilometers per hour, and also we have seen that the total cost of the train to travel 500 kilometers, which is equal to 375 upon 4 into v plus 6 lakhs upon v, and now at most economical speed, total cost at most economical speed is equal to 375 upon 4 into 80 plus 6 lakhs upon, we can take 80. So which is equal to, here we'll get this is 7500, and here on simplifying, so 6 lakhs upon 80 is also 7500. So 7500 plus 7500 will get 15,000. So the total cost at most economical speed to run the train for 500 kilometers is 15,000. So option D. Okay, right. Please like, share, subscribe and support us. Thank you.